Yes, that was the button he was talking about. You know, when you're ready to start, we'll hit that button. You can hit it now. I don't know.
Good evening. My name's Scott Lytle, and I'm the chapter chair for the IEEE EMC Society here in Southeastern Michigan. I thank you all for coming today. So we have a really good turnout. Tonight's sponsors, we have one for the facility, that's Barry Stelz. Barry's in the back. Hey, thank you, Barry, so much. Thank you, Barry. And we have a second sponsor for the pizza, salad, and soft drinks, and that's ZF with Alex Simonoff. So Alex, I don't believe is here today, but we thank him anyway. Yes. In case you're wondering, you do get to keep your NanoVNAs. I know it was only $20, but they were subsidized by your local IEEE EMC chapter. So there you go. This meeting, we're going to try to record on Zoom. However, a lot of it's going to be laboratory type. So I'm not sure what that will do, but we'll do the best we can. At least we'll get Michael's introductions and comments on that. Speaker is Michael Kirkhart. And Michael is an electronics engineer, hacker, lifelong student, and amateur radio operator. During his career, Michael has worked in a factory automation setting, vehicle navigation, and RF testing. He currently works in automotive cybersecurity as a penetration tester. This means he gets paid to hack. How cool is that? During his time as an RF test engineer, Michael used vector network analyzers as part of his daily work. As a result, his homemade SWR bridge, which he used for tuning antennas, has sat on a shelf gathering dust. While not an expert, he is an experienced VNA user, and during this event, he'll provide an overview of VNAs along with specific use cases, all using the relatively inexpensive NanoVNA. Michael.
Oh my gosh. All right. So now we get on to the meat of the presentation. Page down. Come on. Oh, no focus. There we go. Okay, this is the quick who am I? I think we've already gone through this. It's all boring. That's me when I was younger and had less gray hair. Yeah. Yeah, that picture was taken 12 years ago. That's my QSL card, by the way, for those of you who are amateur radio operators, you know what I'm talking about. So the next thing I was going to talk about is like, what's a VNA? I think it sounds like most people here know what this is. VNA, of course, is an acronym for Vector Network Analyzer. And I couldn't come up with a better definition than Alan Wolke. He's a guy he's a YouTuber, amateur radio operator. He's also, I think, the North New Jersey section chair for the ARL. He mentioned that a VNA is an instrument that measures the magnitude and phase of the reflection and transmission properties of the ports of a device versus frequency. And these are instruments that are typically used by RF engineers to measure components, various components of an RF system, including the whole system component. And I took this little picture here. This is from like a Tektronix guide on VNAs, and this is like, okay, what is a vector analyzer and how does it work? And this is probably some nice examples on things you would use it for. Like over here you see, well, there's an antenna. So how efficient is the antenna? How efficient is the antenna? Is it converting electrical power into radiated power? And you see the line going from that to the diplexer is like, okay, well, how much of that signal from the antenna, if it's in receive mode, how much of that's going into the diplexer? This would be like a piece of coax or something like that. So you're like, okay, what's the loss of the coax? And all kinds of other things. You can use it for measuring like the gain of active components. Yeah. Oh, you can't hear me? Oh my gosh, I'm so sorry. Oh, I'm holding the microphone too. Oh, is this better? Okay, all right, thank you. Okay, operator error. So again, these are just some basic examples. And then So now this is kind of like a quick picture of the innards of what a VNA is. I'm not going to spend a lot of time in this because I really want you guys, this is less about, like I said, less about me yakking and more about you guys measuring. So this is I pulled this is from Wikipedia. It shows, okay, there's your stimulus source and it could get routed to either port. Now this would be like for a 2-port full VNA, which the NanoVNA is not. That's what but that's for $100. Okay. And so what it's doing here is you can switch you can adjust the level, which you can't do with this, by the way, but again, $100. And so the stimulus signal will go through a splitter where some of it will go to the DUT. You can see this is, by the way, DUT stands for device under test. If anybody doesn't already know that, most of the people who are in the RF world know, we talk about DUTs all the time. And this is the connection it's making into the DUT here on the input port, and then P2 is the output port. So what it's going to do is send a signal, a known signal in, and then it's going to measure, it's going to look at what's actually going into the port, and then it's going to look at what's getting reflected back, if anything. Now, ideally, if everything is in an ideal world, you're not going to get that. But like as my EMC professor talks about, we don't live in the ideal world, we live in the real world. And so that goes into a receiver here. And then on the output side, you will look at the signal coming back and measure that as well. Now, of course, this is a full 2-port analyzer, so it can switch the stimulus to the other port and do the opposite. And I'll get into a little bit what's all these funny things called S parameters. But anyway, and then there's a microprocessor, and that's got to go Kirkhart numbers. Something's got to digitize these signals and Kirkhart the numbers, and then put all this fun stuff on a display that makes sense. Okay, these are some of the things that are like, I'm taking an example of a 2-port VNA. So I'm talking about, okay, these are S parameters, and I'll get into what these numbers mean if you don't already know in a second. Things like reflection coefficient. From that, you can use this to measure impedances. So typical thing you would do is, like, if you're tuning up an antenna, you want to measure the feed point impedance, and you want to sweep that versus frequency. And you want to see, okay, I want this antenna tuned to work in this frequency band. So you set the frequency range a little bit below and a little bit above. And you go and you look, is it doing it? And if it's not, then you make some physical adjustments, the antenna, trim elements, whatever, and you can in real time see what it's doing. This is one of the things that's so awesome about a VNA, is you can go out there, set up your antenna, cut elements long, set up the VNA, do the measurements, and you can see, okay, here's where we're at, here's where I want to be, cut a little bit at a time, and then immediately see the results. Are we getting closer, closer, closer? And then when you get there, we're good, we're good. You can also measure like S21, which would be transmission coefficient, the transmission coefficient. So this would be like RF amplifier gain, coax loss, filter frequency response, any kind of thing where we're concerned about, like how much is coming out versus what's going in. And then of course, a 2-port VNA can do the same thing the other way. It can go ahead and put a stimulus on the output port and see how much gets through to the input port, and also see how much gets reflected back from the output port. And then we can also do things by using transform, and this is something this is the NanoVNA supports, is we can do this to measure cable lengths or distance to fault or something like that. When you get a reflection back, okay, it can go ahead and figure out, based on the frequency sweep and what comes back, and say, oh, we can turn that into a time pulse, and then figure out, okay, what's that time delay? And if you know the velocity factor of the signal propagating through the medium, then you can figure out the cable length is. That is one of our exercises, by the way. Okay, now we talk about scattering parameters a little bit, and this is kind of like a simple one. I at the end of the slide deck, there's one that's a little more complicated. I'm like, I don't want to present that. And this is just a very basic. So we're looking at like a 2-port, 1-path device, and this SXY. This is the scattering parameter. It tells you like what the response is at port X resulting from the stimulus at port Y. So in this case, like we talk about S11, we're looking at what's the magnitude of the reflected wave versus what we're putting in. And then S21 is like how much we get transmitted through versus what we put in. It's pretty basic. I know you're like, why do they complicate this S parameter thing when it's just like, okay, how much is getting reflected back on the input and how much is getting the output from the input? I don't know. Probably to keep us employed. Mystery. I don't know. And here's a few, these are a few like related S11 related formulas that are kind of interesting. And this top equation is from the definition. You know, sorry, there are some equations in this. Probably should have warned people. And that's based on, okay, what, you know, if you know what the system impedance is and the load impedance, and that system impedance is, you know, reflective of the characteristic impedance of your transmission lines and all that kind of fun stuff. And so from that, you can figure out, you figure out what the reflection coefficient now, because it can measure that reflection coefficient. Then you'll see later on that that's how we can back derive the impedance. And then there's some other ones that are useful, like the S11 log mag. Typically, that will be like 0 dB if you're getting full reflection back, and then anything less than that, it's going to dip down. This is a useful graph for like tuning antennas. You want to see, okay, where the minimum point is. You want to get that down low. That indicates that the load is absorbing energy rather than reflecting it back. The one thing you have to be cautious about, you know, people get really hung up about like impedance matching and all that stuff. And yeah, but the one thing is, you know, you can attach a 50 ohm load to the thing and it's going to perfectly absorb everything, but guess what? That's not going to radiate. So, and then return loss is just the negative of that. That's just another way of explaining. And then VSWR, this is really common within the amateur radio world, voltage standing wave ratio. You'll see these numbers pop up all the time, and your typical, you know, your like MFJ antenna analyzers or whatever will report this number, or even your the meter on your radio will report this. And this is just nothing more than like you know, if you have reflections, what they end up doing is they end up building up, they end up combining with the incident wave, and you end up, if you look at it over time, it looks like you got a wave that's just standing still, therefore a standing wave. And this is showing the formula for how that's computed. And the VNA is doing all this fun stuff for you, you know, based on just like measuring that S11 parameter or reflection coefficient. I'm not going to go too much into this because we could spend a whole talk on this. This is the Smith chart, and this is a graphical way of seeing what impedances are. Because if you think about this, this is like what you're doing is you're taking that reflection coefficient, which is a complex value, you know, has magnitude and phase, and it's limited to being within the unit circle. Because, you know, in theory, you're only going to get reflected at best. You're going to get reflected back as much energy as you put in. Now, if you get more back, then we need to talk. That's interesting because that might be patentable. Yeah, there we go. So anyway, and this just overlays on that. This is what maps, you know, that reflection coefficient to an impedance. These were used back in the days before we had computers and all that kind of stuff, and hand calculating this stuff was a little bit laborious. And so, you know, Philip Smith came up with this chart, very useful, but it's still used today because it's still got that visual aspect, especially like when you're tuning antennas, you can see what the curve looks like. And it's like, okay, when are we getting closer to the center? When does it cross over, you know, the real axis, all that other fun stuff. So anyway, and then bottom, that's if you take that first formula for reflection coefficient and you do the algebra, that shows you how you can solve for the load impedance based on knowing the system impedance and the reflection coefficient. Now we get to the fun stuff. What is a NanoVNA? Okay, this is a low-cost portable vector network analyzer. You know, it's got its own battery and all that kind of stuff. There's a lot of versions of this thing. There's a lot, you know, I didn't want to get into that because that's just all like history and lore. You can go look that stuff up online. I happen to have brought one of my other ones. I have a NanoVNA version 2+4. It's a little bit different, the hardware's a little bit different. It has an extended frequency range, but the software's older. It doesn't do some of the stuff that this one does. But anyway, so that's why I explain you got different vendors, various frequency range, display sizes. Some of the early ones, I think, were like 3-inch displays, and then they start moving to 4-inch displays. Some of them were like just a display on a circuit board and all that. Then they start putting them in cases and all that stuff. Then they started adding, you know, SD card slots, all that kind of stuff. So these are typically like 2-port 1-path measurements. So we're talking about like measuring S11, you know, where it's putting stimulus on port 1 and then looking to see what comes back on port 2. And then you get this very low cost, you know, I don't know how precise this is, the calibration kit. This is what like you can actually spend thousands of dollars on a VNA Cal kit, believe it or not. And it's just a manual one. You know, you want to really spend some money, get like one of the electronic Cal kits. Those are actually awesome. There's no switching out of anything. You connect your leads to it and just press a button on the VNA and boom, it does everything for you. So the last item there, again, not nearly as capable as a professional VNA. You can't do full port, 2-port, 2-path measurements, can't adjust stimulus power. That becomes important if you're measuring active devices. But for $100, like for a typical VNA, I'm kind of guessing, like I know in my old role, we had one of these Keysight Field Foxes. These are really cool. But this one I think was around $40,000. Typically you can spend like $50, $100, or even $500,000 for like one of those fancy Rohde & Schwarz 4-port VNAs. Those will do all kinds of really cool things that I haven't really even gotten into, like doing things like linearity measurements, like finding, on amplifiers, finding P1 dB points, or doing, intermodulation distortion measurements and all that. But $100, you can do a lot with this $100 NanoVNA. That's why these are so cool. And how this performs measurements. I think somebody, you who was asking about this. Okay, so this is kind of a block diagram. Now there's full schematics available because that's the other cool thing. This is an open source design. The schematics are available, PCB layout, source code for the firmware, all that kind of fun stuff. And this is just a block diagram of how they built this. It's centered around, one of these STM32 microcontrollers and a display and one of these adjustable oscillators. And how they're not using a directional coupler for measuring reflected power. They're using like an impedance bridge, but it works. And then here you got the mixers to down convert the stimulus and response down to something to a lower frequency. I don't think these things go all the way down, right down to baseband. I think they have like some low intermediate frequency that then is digitized and then looked at by the microprocessor, and a bunch of numbers come out and then decides, okay, I'm going to display this. You got a couple of user controls, push button, switch, all that kind of stuff. It's actually like a little jog wheel that pushes in on there as well. And it does USB. It's got USB connectivity, so you can connect this up to software like NanoVNA Saver or the NanoVNA app or whatever. And then of course it's got LiPo battery that you can charge as well via the USB connector. So this is what the user interface looks like on one of these things. You guys have probably all powered one up, or probably a bunch of you already own them. There's the main display. You got a legend of traces. It can display up to 4 different traces. You can get to select what you want to display. Here's the port 1, port 2. It shows you calibration status. So it tells you like, okay, have you gone through each of the steps with the open, short, load, isolation through. Down here at the bottom, it shows you like your stimulus information, like your start frequency, your stop frequency, the resolution bandwidth or IF bandwidth, which is fixed. You can't adjust that. That's something you can adjust like on a high dollar VNA, but again, $100. And it'll tell you how many points are in the acquisition. Now this one will actually, like a lot of them, will only do 101 points. This one will actually do 401 points in an acquisition. But the price you pay for that is a longer acquisition time. If you want to try this, we will do the calibration with the normal 101 points. And then if you want to try it, do it with a 401 and see how much longer it takes to do each step. But if you need like a wide frequency range, but you want good resolution, that's the way you do it. And then here's the main menu. Now each one of you guys probably got, there's a piece of paper. Oh, that's right. I'm not at that point yet. Here's some more of it. So I'm getting ahead of myself. So here's the top part. You see the jog wheel, the on-off switch, and then there's a micro SD card slot. Now you can use this for saving screenshots. This will also save like your S parameter measurements in touchstone format. So if you want to bring this into a computer and do something else with it, or use it with software like Python, the scikit RF stuff or whatever, it'll generate those files for you. There's your these ones are using a USB-C port for charging and interface. And then there's a little LED indicator there And this little hole there that indicates when it's charging. Okay. There we go. So you're looking at this like, oh my gosh, there's a lot there. We're only going to be touching like a small portion of this, though I know some of you guys brought DUTs that are going to start touching some of these other things, but I'm not going to stop you. Please do it. And then once you get it working, show me so I can learn. Because I've actually not actually done any component measurements, but that's something else you can do with this, is you can actually measure, you can get component measurements like inductance, capacitance, all that kind of stuff, or potentially like on a capacitor, you can measure ESR, things like that. But anyway, you guys have that chart comes with every one of these. And then now I'm going to talk about calibration. So why do we need to calibrate a VNA? And it's really kind of like two reasons. You got to compensate for systematic errors, and then also you got to compensate for your user measurement configuration. So when we're talking about systematic errors, we're talking about like the imperfections in the device, because it's got to operate over a wide frequency range with wide dynamic range. Yeah, the matching on the input and output ports, it's good, but it's not perfect. You've got the direct, in this case, the impedance bridge. There's going to be some of the direct signal that gets, the forward signal, it gets through on the reverse. It's not perfect as well. And then as far as the ports, you don't have like perfect isolation between them. There'll be a little bit of crosstalk depending. So, and then of course the frequency response of the receiver, and even the signal source is going to vary, will vary over your frequency range. So you got to be able, you need this calibration step to kind of like get all, to compensate for all those kind of things. And then as far as the user, this is like, okay, all the cables, the fixturing you got to go to get, to get the signal connect from your VNA to your DUT. And always the desire is that we talk, in the VNA world, we talk about the measurement planes. Now that talks about like the cross section of where the signal flows through. And you want that to be kind of like right at your DUT. If it's not, then what you're measuring is not what's going on at the DUT. And I've actually, I didn't do a slide for this, but I have an example where I've got like a board with a 75 ohm resistor, but it's got some extra leads. So now if you cal it just at the cables and then connect over that extra cable, the extra cable length from the adapter to go from the SMA to the UFL connector that's on the board is going to introduce some error. And so things that you see, don't make sense. But anyway, so then, here's when do we need to calibrate it? Okay, like when you power it up, whenever you change frequency range, you should recal it. When you change any of the cabling fixturing, you need to recal it to reestablish that measurement plane points right at your DUT. And then another possibilities, like if the operating environment, okay, you're in a warm room, it's getting warmer. I know it's a temperature controlled oscillator on this, but the temperature controlled means it's okay, somewhat compensated for that. It's not perfect. So if you start looking and you see things look a little weird, maybe you need to check, at least at the minimum, check your cal. And I'm going to go going through both of these. So now we're at the point where we're all going to do this as a group exercise. We're going to calibrate our VNAs. So if you guys could go ahead and power them up if they're not already. You can go ahead and connect the cables to them as well, because you're going to need them. And the funny thing is too, we're going to be using the through calibration standard as an adapter. Because you notice the cable, the cables themselves are SMA male on both ends, but the calibration standards are also SMA male. And when I first saw that, I'm like, what? But I'm like, okay, this will work. So I'll give everybody a few minutes. I don't know does anybody have any questions while we're at this? Yes, sir. Okay. I know DUT is device under test. EUT has got to be probably equipment under test. Lucky guess. Okay. I don't know, is there ever? Yes, sir. Uh-huh. Well, that's always a yes, you're correct. That's always a possibility. Uh, I it's funny because you look on the websites for these things and they'll all claim, hey, look, we're we're the official developer of this or whatever of this particular version. A lot of times they'll have recommended sources to buy them from. Where they say, hey, if you buy from these guys, this is a genuine, this is something we built. Um, that's about the best advice I could give you is like buy from a reputable seller if you can. I can't speak to these. Okay, good. Or just NanoVNA groups. It's on groups.io. Yeah. Okay. Everybody kind of at this point? All right. So to do this, you're going to need to go to the calibration menu. So like from the main menu, you hit calibrate and you should see a screen that looks like this. Make sense? Anybody? Okay. And then if you hit the reset button, that will reset the calibration. So I've already done that, like in this case, and you can see that all the calibration indicators have gone bye-bye, which means it's like, okay, it's no longer calibrated. Because normally when this thing powers up, I believe it's going to use whatever calibration was saved in slot 0. And I think that's the one that they use for factory test. We good? Okay. And again, if somebody needs help with this somewhere, they get stuck somewhere on the way, I'll come by and help you out. And then now the next thing is like the calibration open. So what you want to do is with the through adapter on there is go ahead and take the open standard. And you're probably like, which one is the open? So if you pull these calibration standards out, that's the load. That's the short. So the open is the one that doesn't have a pin. Okay. I mean, I thought, but I just covering my bases. So once you go ahead and connect that up to the port 1, not port 2, port 1. Once you have that, then what you'll do is, well, the next thing you'll do is you hit the on the calibration menu. Let me go back up here one. See, when you're in this menu, when you hit calibrate, then what that'll do is it'll bring you to this menu over here. Is everybody able to get to that? Okay, so once you have the open standard connected, then press open. Okay, and what you'll see is you'll see like some progress bar come across or whatever. And when it's finished, you'll see a check mark on there and it'll automatically kind of like go to the short. So the next one, as you can probably guess, is the short. Now, I'm assuming you guys can figure out which one is the short. It does have a pin on it. Yeah, exactly. So once you get that connected, then go ahead and just press the short button. And if all goes well, you'll see that you'll see it get checked off. Everybody okay? Am I going too fast? I'll give a minute. If somebody's got a question or they're hung up, I'll try and help you out. Oh, no, it's port one. See, when you're doing, again, this is a 2-port 1-path device. So there is no, it doesn't do any reflection measurements on port 2. So everything's on port 1. You are in the right port.
Okay. No,
But that is a very important point, because like if you were doing this on a full 2-port VNA, you'd have to go through this whole procedure also on port 2. And you'd have menu like, okay, port 1, connect, it would tell you connect open standard to port 1, and the short, and then the load. And then it would say, okay, connect the open to port 2 and all that. And then it would tell you to connect the through and do the through calibration. Yes, we don't have to do that, fortunately. Question, anybody? Yes, sir. We good? Yes, you do. No, so to do the isolation, you're getting ahead of me, but that's okay. To do the isolation, what you'll do is you'll connect the load standard to port 2. And what you're doing there is because it's measuring, how much the crosstalk from, okay. Yeah, I was a little thrown by that first. What's this isolation thing? I've never done an isolation on a VNA, but again, I think this is kind of a quirk of the NanoVNA. So it's like, okay, I can do that. And the cool thing in the order is once you do the load on port 1, then you just take the load standard and connect it to port 2, and then click isolation, and then you're good. All right, so everybody got through the short, or at least understand it. Okay. And so now we go to the calibration load. Now, by process of elimination, you should be able to figure out which one the load is, right? It has a pin, but the pin isn't like connected to the shell. And if somebody has an ohm meter, they can check it out. It should be 50 ohms. And once you connect that, then you would press the load button and it'll do a measurement on the load. Yep. So if you are getting ahead of me and you're doing isolation, once you've done the load, you just go ahead and move the load standard to port 2 and hit isolation. We good? Sort of? Which one's what? What are you looking for? The load is this guy right here. It does stand up because it's a little bit bigger and it's got a pin, but you can see the insulation on the middle. We good with load? Okay. Now we do isolation, and all you need to do here is, like I've been telling some of the other people who are getting ahead, is like just take that load standard and now move it over to port 2 and then hit isolation. Everybody good? Anybody got any questions? Yes, sir. Oh, that's okay. That's okay. You're about to do the through, right? So there's the through. You just take that, you take, the RF adapter, the female adapter, I mean the through calibration standard, and connect port 1 to port 2. And then you just hit through. It hasn't applied the calibration yet, so if things look funny, it's okay. As soon as you apply it, then it'll correct. And as a spoiler, we're gonna, after we do this, we're gonna do a calibration check. Don't worry about it. If the graphs look funny, it's okay, because it hasn't applied the calibration as of yet. Okay, so now we've done all the steps, and now all we have to do is press done. Now, what this is going to do to us is going to ask us to save our calibration in one of the save slots. And you just pick an empty one if you want and click on it. And once you do that, it will then apply the calibration. And then all of a sudden, this thing should magically look reasonable. Wow, awesome, that worked. But we're going to do a check. And the check is good because, like, if you see some measurements that look funny, then you can go back and like, well, is the calibration okay? Then you can go through a quick step of calibration. You don't have to press any buttons when you do the calibration. You just connect up those calibration standards and look for certain things on certain graphs. Okay, have we applied this calibration? We good? Okay. So we've saved it. Awesome. Now, how do we verify the calibration? Now, some of this over here, you'll see it shows that everything's applied and it shows, okay, it's using the calibration that we've saved in slot 2. I'm trying to remember all these. It's not open short load through, but this is like directivity, reflection, and I can't remember what the S is, but the T is through, and then the X is isolation. And they're all showing there. So that indicates that. So now to verify the calibration, what you can do is take off, if you got the two connected together, just remove the connection and put the open back on. And then what you should see, if you've got S11, which I think these things all default to having like trace 3 as S11 Smith, then you just look on the Smith chart and you should see a dot over here on the right side of the Smith chart. Everybody kind of seeing that when they do that? You're probably already seeing something close to that without the open standard connected because it is kind of an open already. Huh? Yeah. Is that what you're seeing? Yeah. Oh yeah. Yeah. Oh, okay. Yeah. Well, it's because it's got the marker turned on. Okay. Everybody kind of see that? Okay. Now, if we want to verify the short, you just put the short, standard on, and guess what? Boom, it goes all the way over here. Anybody got any questions, concerns? Are they having trouble with anything? Did you print out my slides already? How'd you get those? There's plenty of guides on how to use this thing out there. So, and they probably did a far better job than I did. Yes, sir. Okay.
So the S11, that's supposed to be a ratio.
Yes, it's a ratio. In the end, it's the ratio of the reflected power to the incident power.
Why would a short?
Because you're still getting reflection, but it's the other way. If you go back to the formula, you'll end up getting a reflection coefficient of -1 or -1 plus 0J. But the magnitude is still 1. So it's still going to be on the other side of the Smith. And that corresponds to a 0 ohm impedance. That's why it shows up on the left. Later on, I can go back through the Smith, the equation, the S11 equations, and show you how that works out. Okay, we good with that? Now connect the load up. Anybody have an idea where this might go? Yeah. See? You guys should be putting on this presentation, not me. You know all this stuff already. So yes, you are correct. You're laughing with me or laughing at me? Either way, it's okay. Okay, we good with that? We just have one more check to do. And this involves using that through connection. We probably should have done this first because we already had it there, but whatever. Get used to this. So if you're using a regular VNA without an eCal module, you're going to get used to like swapping calibration standards all the time. Yes, this is your life. It's like, okay, I spend 10 minutes calibrating and 30 seconds doing my measurement. But that's the way. If you're doing tests, everybody knows the most of the time is the test setup. Once you get the test setup there, you do your test, and it's like over within 5 minutes, but it take you 4 hours to do the setup. Situation normal. Okay, so now when we have the through calibration standard on, we're not so concerned about the Smith chart, but it should be still in the center because again, the port 2 should be terminated in a 50 ohm load. So it should be a pretty good match. But the things you want to look at are the S21 log mag. So this should be pretty close to 0 dB or something like it. Something within decibel dust, as one of the members likes to call it. And then if you look over here at the S21 phase, it should be like at about 0 degrees or something close. Once you get through all that, then it's like, okay, I got a calibration. I got a measurement plane that's right here at the connectors. Now I can go forth and measure DUTs. And guess what? We get to go. Oh, yes, you have a question? That's okay. No. That's.
I was expecting with the calibration for the logarithmic S1 to be flatter.
S11, yeah, well, again, when you get down below, like if you get like an S11 log mag below, like say 20 dB, that's a pretty close match. And you're seeing now you're starting to see the imperfections in the system, potentially in the VNA or potentially in probably this is more has to do with the calibration standards and the cable and all that kind of stuff. Remember, now the default is like 10 dB per div. So no, it doesn't show you that. And this is another one of the, maybe not so, this is adjustable though. And if you want to see that, here, let's do like a teachable moment here. So if you go to, yes, it is. It shows you right there. It's like 10, it shows you it doesn't show you like on the, I would have liked it over here on the left because that's the way I'm used to working with normal instruments. Yeah. And you can adjust that if you go all the way to the main menu and you go scale, trace, and then there'll be like it's display, trace, scale. And then you can enter in like a number, like if you want to make it like 5 dB per div or even 1 dB per div, you can. Okay, we've verified calibration and all that fun stuff? Okay, cool. So now it's time for me to stop yapping and for you guys to start measuring. So I've got a number of DUTs here that I brought with me. I've got like various antennas, cables, and stuff like that. Unfortunately, I don't have as many DUTs as we do attendees. So what you guys will probably want to do is group up in like groups of 4 or 5 or whatever, and then go through this setup on some of these and actually do the measurements. So, again, I purposely had you guys calibrate with like unknown. I didn't remember, I didn't tell you what to set the frequency scale to, but that's going to give you exercise in calibration because you're going to need to set the frequency scale, calibrate, and then set up traces. And this one, all you're going to do is make some adjustments to the base, the existing default traces, and then measure antennas. So I've got like 4 different antennas. Or actually, I got a fifth. I got a mystery dot, which happens to be one of these. And I pulled it out of the dumpster at work, and oh yeah, I was just kind of curious. And it's like, okay, it's an antenna. It's like a quarter weight, a little monopole of some sort. You can measure up the length and figure out kind of where it should resonate at, but then you can measure it. So I've got antennas, I've got coax cables that we can do. I got some simple stuff, like you want to do some simple S21s that are pretty predictable. I've got some like inline RF attenuators that you can go ahead and measure. I've got various lengths of coax cable that we can do we can do S21 measurements. We can measure like cable loss. I've got a particular homebrewed 2-meter bandpass filter. And you can, I had an idea of how it was supposed to work, and you'll get to see how it actually worked and why I wish I would have had one of these things when I built it, because then I would have known rather than guessing like, is this thing working? It doesn't look like it's working. And then I've also got I've got a piece of cable. Well, any of these pieces of cable, we can go ahead and do a cable measurement. Now I didn't explain, well, I've got slides that explain how to set up to do that. So anyway, that's kind of me. I'm kind of done yapping. And what I'll do is I'll walk around, answer questions, whatever. I'll put some of these duts out here on the table. You guys can like grab them and start measuring. This is one of the duts as well, by the way. This is one of the first antennas I built after getting my amateur radio license in 2011. This is a 2-meter tape measure Yagi. Now, the one thing I will ask you to do is be careful, because that tape measure, the edges, they're not super sharp, but I don't want anybody getting caught. I did put tape on the ends, so, hopefully nobody, but be careful. Don't poke your eye out, please. So we just learned something today. So it turns out you can get like a display on the side that shows like the scaling for some of the graphs. And you go to the display, or it was a display, trace, scale, and then on the scale there's an option to show. Uh-huh. Uh-huh. Okay, so it's display scale and there's a checkbox to show grid values. For some reason, it's turned off by default. But you can turn it, or maybe they wanted to, they've already got quite a cluttered display because you're showing 4 traces on, one screen. So they turn it off by default. But when you turn it on, now you can see this, you can see at each grid line what the represented value is. That's awesome. I didn't know that. Now I do.
So between these 2 steps here, where we connect the load and calibrate,
Mhm.
when we just leave that load connected to channel 1.
No, you connect it to channel 2. Did it say channel 1? Because that's not correct.
Well, here it says, yeah, there's only one load, black load, standard ports, one.
Really?
And port 2 to channel 1. I was wondering.
Oh, that's not the way I learned it. But I guess if it kind of works.
So it's kind of like.
Oh, grab a duck.
So at first I was kind of thinking like, I don't think that was in your steps there, but reading this here, I kind of like left the load. And I put the load on, quick load, that check, and then I'm thinking leave the load on there and do the ice.
Okay, because I mean, the way I learned it is I took the load and put it on port 2 and then ran the isolation because what it's doing is checking to see is there crosstalk going on between port 1 and port 2, and this will terminate port 2. Yes.